Assalamu alaikum, dear students. I'm very happy to be back with you with another video lesson. In the previous video lessons, we did talk about Lenz's law, we did talk about Faraday's law of electromagnetic induction. We're going to still talk about electromagnetic induction, but this time we're going to talk about self-induction. So what is self-induction? We're going to dive into this a little, and then of course after that we're going to solve a few questions related to these, of course. Now, what is self-induction? We can say self-induction is basically the creation of induced electromotive force in a circuit due to its variation of its own current. So what does exactly this mean? Now, so far we've learned using Lenz's law, of course, we said when a magnet, let's say, brought close to a coil, what will happen? Of course, there will be an induced current in the coil. This induced current will have its own magnetic field. These two magnetic fields, of course, oppose one another. That is basically Lenz's law. And of course, Faraday basically tells us the magnitude of the induced voltage, let's say, or the electromotive force. Today we'll talk about the induced electromotive force, which basically when the current on a coil, let's say, it is changing. This change on of course, there's a magnetic field around this coil. When the current is changing, the strength of this magnetic field varies or changes. And this change, of course, leads to an induced electromotive force within this coil itself. And of course, this is what is called self-induction, because there is an induced electromotive force inside that coil here. So let me tell you what exactly happens. Now, imagine or consider that we have a battery, let's say, and then we have, let's say, a coil here, or it could be a solenoid, for example. And then, of course, we have, let's say, for now, let's say we have a switch, okay? So remember this. This is basically positive, this is negative. Let's draw a coil here as well. So let's say this is a coil. All right. So this is what we have, and then, of course, it goes all the way there. So this is basically what happens when we have this. We know that current goes, or let's say when we close the switch, of course, current flows through the circuit. And when this happens, of course, here's the direction of the current, which is basically in the direction, or conventional current, that is in the direction of positive charges, you can say. So if that is the case, of course, current will be flowing through the circuit. And of course, when current flows through the circuit, there will be a magnetic field around this, this coil or this solenoid, you can say. And of course, using Lenz's law, we can tell the direction of this magnetic field, you can say. So of course, you can see here the direction of the current is going like this. Of course, it goes like this one here. Okay, so if that is the case, you can see that this side is going to be north, and then the other side is going to be south. Let's say these are the direction of the magnetic field lines here. Okay, so this is basically what happens when we have a battery connected, let's say, in a circuit connected, you can see, to a solenoid as well. Okay, so this is basically what happens. But now let's talk about self-induction and what is exactly self-induction. So if we go back a few steps here, this is basically what happens the moment that we turn the switch on. Remember, the moment that we are turning the switch on. So when this happens, we do know that there will be a magnetic field induced, you can say, or when current starts to flow through the circuit, magnetic fields, because current is about to increase, yes? If that is the case, through the coil, of course, or the solenoid, if that is the case, then of course magnetic fields are starting to form around this solenoid. So if that is the case, you can see that. So this is the first moment that this happened. And then of course the second moment, you can see that there is a change in the magnetic field, yes? These magnetic field, like we said, this is north, this is south, so these are the direction of the magnetic field. Okay, so far you agree with me, yeah? Because you've said it all this. Now, as you can tell here, as the current started to, let's say, flow more and more, there was a change, there was a variation of the magnetic field. But we've learned before that when magnetic field is changing, and of course if we have a conductor, there will be an induced electromotive force. So we can say within or inside this solenoid here, so if I draw or redraw the solenoid one more time here, there will be an induced electromotive force as well. So let's say this is the solenoid that we have. All right, and of course it goes all the way there. So the moment that these magnetic fields are generating, you can see that there was a change or variation of the magnetic field. This variation of the magnetic field will also induce a current. Remember this, induce what? Induce a current within this coil here. So if this is the direction of the current that we have, basically, this is the direction of the current, there will be an induced electromotive force, or an induced current, electromotive force first, you can say, and then of course a current which is going to flow in the opposite direction based on Lenz's law, don't forget, okay? And of course we know that this current, if the current here, it is flowing this way, the current there, it is going to flow in the opposite direction here. And of course the magnetic field that we're going to have, it is going to be like this, yeah? This is going to be north, this is going to be south. You can say, oh, my bad, not this one here. Okay, so if that is the case, yes, if that is the case, it is going to be moving, it is correct. Right? So this is the direction of the magnetic field. You can see that these two are in opposite direction, so we can say these two will be opposing one another. If that is the case, and as this one, or the change, the variation of this one gets bigger and bigger, of course, we can say this induced electromotive force will also gets bigger and bigger, so of course we will get a bigger opposition here as well, okay? So we can say here there will be, as long as there is a change in the magnetic field lines here, there will be an induced current. This induced current will have or produce its own magnetic field. Now these two magnetic fields, of course, oppose one another, by the way. Okay, so if that is the case, or the induced of this electromotive force and current, you can say this is what is called self-induction, by the way. So this happened within this coil right here. So why does this happen? Why do we get this? Because the magnetic field around this one here, it is changing. Or you can say the change of the magnetic field in this coil, of course, it arises or generates this magnetic field. Okay, so now that is basically when we turn the switch on, yeah? So what happens when you turn the switch off? If you turn the switch off, of course, you can see that this magnetic field line are going to, let's say, reduce one by one, let's say. If that is the case, we can say this, there is one more time, there is a change in the magnetic field line as well, yeah? So it's almost like if you are moving this magnet away. If that is the case, of course, this one also, there is a variation, there is a change in the magnetic field within the solenoid. So this time again, a current will be generated or induced, let's say, or let's say electromotive force first, and then there will be a current here, but this time the current, obviously it is going to move or flow in the same direction as before to resist, to oppose the decrease in this current here. Once again, there will be a magnetic field, but of course the magnetic field, when it is decreasing here, is going to be like in opposite direction to the first one here. So of course you can say the current as well is going to be flowing in the opposite direction as well. So this is what we get as a result. So this, you can say this magnetic field will add up to this magnetic field, hoping to keep the total the same. This is what happens, or what we call self-induction. It is an induced electromotive force that creates within the same coil that we have, but as a result of what? As a result of change in the current, you can say. All right, so in order to do this one, or constantly have this changing, instead of turning the switch on and off manually, we can have something different. Instead of all this, we can use a variable resistor here. So what does this variable resistor do? Normally, resistor resists the flow of current. That is, I mean, we do know this one, yeah? And of course, we do know that using Ohm's law, V equals to IR, yeah? So you can see here, current and resistance are, you can say inversely, you can say inversely or inversely proportional to one another. In another word, that by increasing the resistance, the current decreases, and of course, by decreasing the resistance, the current increases. So what is the benefit of this? By increasing the resistance or decreasing the resistance, of course, the strength of the current that is flowing through the coil changes. And if the current or the strength of the current that is flowing through the coil or the solenoid changes, that means the magnetic field around this solenoid is going to change. So as long as there is a change in the magnetic field, there will be an induced current inside this coil here, and of course with it, which is the same coil, by the way, okay? So as you can see here, when this magnetic field lines are around, or when the current changes, the magnetic field or magnetic flux, you can also say that, around the coil is changing here. This change of the magnetic flux or magnetic field lines, of course, will lead to an induced of you can say an induced current. This current that is obviously induced will have its own magnetic field, and of course these two magnetic fields will oppose one another. By the way, in terms of, we can say, in terms of increasing the current that is basically flowing through the coil and the current that is generated or induced through the coil, these two current will be in opposite direction. Remember this. So the current that is induced, this is induced, and this is the current that is flowing through the solenoid. In terms of when the magnetic field is increasing, let's say when the current is increasing, this one try to oppose this one, okay? So this one, you can say it is induced here. Okay, but what happens when you let's say when you increase the resistance? If you increase the resistance, the current decreases, and then this magnetic field is going to decrease. There is a change in the magnetic field. This change, of course, in the magnetic field or decrease in the magnetic field, it is the same as if you move a magnet or as if you had a magnet moving away from the coil or the solenoid. In this case, of course, this current is going to decrease, but of course this current will be in the same direction that is induced so that it can make up for the reduced current so that it can keep the total the same, you can say, or at least for the magnetic field to keep it the same here. So this is what happens by doing this. So basically whatever that I drew here, basically it happens within this coil so that you can see what happens here. This is what we have and this is what is induced here. So this process is what is called self-induction. Okay, but of course the one that we have in the book is quite a little bit, I mean, you can say it a little bit different, but the principle or the base of all this is basically the same. So what do we have for this one or for this self-induction? You can see that we have a battery, we have a switch, we have a rheostat, or you can call it variable resistor. You can see we have coils, and of course we have an ammeter or galvanometer. That is basically, we use them, or we use that as an ammeter right here. So what do? We'll have a certain current through the coil, through the circuit here. It could be any current that we have, let's say. Okay, the book says, for example, assume that it is 50 milliamperes, let's say. So once you have this current within the coil, it could be any values, by the way, as long as, what is the purpose of this? The purpose of this to have a set of, let's say, a certain value of current, and then of course we can, let's say, add the coil or remove the coil. Once we do this, of course, then there will be an induced electromotive force, and then of course we can see the effect on this ammeter right here. So you can have any value for the current that is within the circuit, and then after that, of course, what do? Of course, you can adjust this one by this rheostat or variable resistor here. Okay, and then when the coil is connected, so basically we have, let's say, a certain magnetic field within or through this coil. But once you connect the coil, let's say, for example, then of course now current is, or you can say there is a magnetic field around this coil here as well. But remember, when magnetic field lines are generating through the coil, that is for the circuit, let's say, then of course, as a result or as a response to this change of this magnetic field around the coil, of course, you can see that there will be an induced current. This current that is induced within the coil, or you can say it has its own magnetic field line. So these two magnetic field lines oppose one another. So what happens when these two oppose one another? If I take you back to this one here, we said that the current in this two, of course, is going to be in opposite direction. That is in terms of increasing. If current are in opposite direction, of course, you subtract them. So you see that the ammeter, so if we add an ammeter here, you see that the pointer in this ammeter or this ammeter reads a current, or you can say a lesser current. Now why? Because these two oppose one another. As a result, the current on the main circuit will be less. That is for this. But what happens when we remove the coil? If you remove the coil, like we said earlier, it is as if you are using basically a magnet, and these are you going to remove the magnet. If that is the case, then of course this electromotive force, or you can say the magnetic field, is decreasing. Again, there will be an induced electromotive force within the coil because the magnetic field line is changing, if that is the case. But then this time, the current that is generated will be flowing in the same way as the current that is in the circuit here. That is basically the second time, yes? And if that is the case, this too, or this is induced, so of course will be added up to this one so that it can keep the total the same. And you see that when we turn, or you can say when we remove the coil, in this case, the current of, or on the ammeter, let's say, it is going to increase, indicating that, of course, you can see that the current that is induced within the coil now that is going to be in the same direction as the current that is on the circuit, let's say. So that is what happened when the intensity, when the coil is removed, the current increases, the magnetic flux decreases, you can say. And the intensity of the current is, or you can say when the intensity of the current is increased or decreased, you can say the magnetic flux crossing the terms of the coil will vary. So as long as you're moving, increasing or decreasing the current here, there is a change, a varying in the magnetic field around the coil, or you can say the magnetic field lines that cut through the coil. And of course, as long as you're doing this, there is an induced current, current that is generated. This current that is generated will have its own magnetic field. So these two magnetic fields will oppose one another in case of increasing the current in the circuit. And of course, they are in the same direction in terms of decreasing the current of the circuit. So this is what you see, that the galvanometer reads a higher current or a lower current in terms of, let's say, let's say increasing the current within the circuit, it reads lower. But once you decrease the current, of course, let's say by increasing the resistance, this galvanometer reads a higher value, or the ammeter, you can say. So this is basically what happens is a self or a back, let's say, electromotive force that is created when the current increases, and it is proportional when the current decreases. So when the current is increasing, the current that we have on the circuit and the current that is basically generated, or you can say induced, this will be opposing one another. As a result, this reading will get lower. All right, so on proportional, you can say electromotive force, and of course, what leads to a higher current as well when the current decreases here. So when the current on the circuit decreases, the current that is induced here will try to flow in the same direction so that to keep the total the same, which in this case, you can see the galvanometer or the ammeter, of course, reads a higher value. So we then deduce the following. If the magnetic flux through the coil is varied, is changed, due to the variation of the current in the coil, then this variation affects the coil and leads to an electromotive force that resists the variation of the original current of the coil itself. This phenomenon is called self-induction. So what is self-induction, or how we can define self-induction one more time? So remember this, self-induction is the creation of an induced electromotive force, okay? And of course, in a circuit, due to it is, let's say, own variation of its current, you can say. Now we have a study tip, remember this. It says the self-electromotive force is in the opposite direction when the current is increasing, okay? And of course, it is in the same direction when the current is decreasing. Remember, so we can say there is an electromotive force induced. This electromotive force induction, of course, leads to a current induction. This current or induced current, this induced current, of course, will have its own magnetic field, which it is opposes the original or the circuit's magnetic field, we can say. Okay, now watch this one. It says, in order to calculate the self-electromotive force, we assume the following. So remember this. One thing before we proceed was this. We said as long as there is a change in the magnetic flux, there is always an induced electromotive force, you can say, yeah? Or you can say a current will be induced. So we can say, based on this, we can say if the current traverses in a coil, if a current passes through a coil, the magnetic flux, okay, which crosses each turn of the coil is directly proportional to what? To the intensity of the current. We've learned this one before. Let's say if 1 ampere passes through the coil, of course, you will have a certain magnetic field. What if you increase that current or the intensity of that current, make it 2 ampere? Of course, 2 amperes. In this case, the magnetic field around the coil or the solenoid, of course, it gets bigger or stronger. All right, if the current varies at a rate of, so if we change the current at a rate of, let's say, delta I over T, that is the change in the current, of course, per unit time, we can say the flux, the magnetic flux, will also varies at a rate of, let's say, magnetic flux or delta flux over the time. And this is directly proportional to the rate of the variation of the current. And of course, this process would lead to an induced electromotive force. Okay, that is, or you can say, a voltage generation. All right, so based on this, we can say that, of course, the flux it will be, or the change in the flux, let's say, will be directly proportional to the current. And then, of course, we can say, watch this one here. We can redraw this one, by the way, but let's just redraw this one more time. Okay. Let's see how it is done. Okay, so watch this. We said, basically, this flux is directly proportional to the current here. correct? Now, of course, we can say that if we divide both sides by the time, of course, we will have what? We will have change in the magnetic flux, all right? Or we can say, of course, the change in the magnetic flux divided by the change in time, or delta t. Of course, it is going to be proportional to the change in the current divided by the time as well. And of course, if we're going to multiply both sides, because if we have n turns, obviously the coil or the solenoid that you're going to use is going to have a number of turns. So if we are going to multiply by this, let's say by negative n, so we will get something like this. So in this case, of course, we get negative delta flux over delta t, which is basically proportional to what? Which is basically proportional to n, or negative n, basically delta I over delta t here. Okay, so far, isn't this term a little bit familiar to you guys here? So yes, it is, yeah? Or before that, of course, now, if we want to use this one as an equation, we can say negative n delta flux over delta t equals to, because we're trying to get rid of this directly proportional. And if we're going to use an equation, of course, you have to use a constant to represent, or you can say, so that we can say equal to, yeah? So in this case, we can say equal to, for converting, we're changing this one, then of course we must have a constant. So we'll say n, or negative n times a constant equals to what? You can say multiply by delta I. This is delta I as well, but, right? Now it's better. Delta I basically divided by delta t. Now instead of all this here, we can write a constant here. So in this case, we can say, so remember this, negative n delta flux, or change in the flux over the time. Instead of all this, we can have something else, of course. We can have, let's say, L, which is basically, or negative L, we can say. Remember this n times the constant. Now we're using this L here, which is basically the coefficient of self-inductance here, multiplied by delta I over delta t. But you've already learned that this part equals to what? It equals to the electromotive force, correct? So we can say the electromotive force that is induced equal to negative L, that is delta I over delta t. Okay, now of course if you want to, by the way, once again, this one is the coefficient of self-inductance here. If I want to find the, or make the coefficient of self-inductance as a subject, I can say L, coefficient of self-inductance here, equals to the electromotive force, and then divided, or negative, divided by delta I. Will just bring this one, the whole thing under this, so delta I over delta t here. By the way, the coefficient of self-inductance here, that is basically measured in Henry, okay? And then this one is basically measured in volt, and this is measured in ampere per second here. And of course, we can take the second, by the way. So this is the equation that, or the two equations that we have. Remember this, the electromotive force, all right? If we have a, let's say, self-induction, this is the equation that we're going to use. That is, let's say, for coil if you want to. And of course, we will have the coefficient of self-induction for solenoid as well, but just remember this one for now. The electromotive force generated or induced equal to negative L delta I, or the change in delta I, let's say, over delta t. Now this is basically the coefficient of self-induction, that is electromotive force, and then delta I over delta t. Now we can work out the unit of this one, or we can say what are the unit or other units that we can have for this one here. Okay, watch this one here. So instead of all this, let's erase this a little. There are a few things you need to know, yeah? And of course, these are very important. So instead of all this, we can say, watch this. We can say Henry is basically equal to what? As we said, equal to voltage, all right, over ampere, because that is current, over the second, yeah? So I can take the second up. So I can say Henry is equal to what? Equal to voltage over ampere multiplied by second as well. But you do know that using Ohm's law, voltage equal to current times resistance, yeah? So this is volt, this is ampere, this is ohm here. So if we move this one under, of course, ohm equals to voltage over ampere here, okay? So now instead of this one here, we can say Henry equals to ohm multiplied by second here. But we do know that, all right, this second, it can be written here, or at least this one here. We know that frequency equal to 1 over t, yeah? Or you can say hertz is basically equal to 1 over the second. So as you can see here, at this point here, I can write this one Henry here. I can write it as, let's say, volt, ampere, and of course multiplied by hertz as well, you can say, yes? Not this one here. We can say the hertz would be below here. Okay. Now this one too. That is this. So you've learned that we've moved this one up as well, so we can write that one too here. Now, if I want to find the unit for ohm, I can also say ohm, of course, is equal to, we can say it is equal to Henry over the second as well. But Henry over the second, it's almost like Henry multiplied by 1 over second. And isn't this like we can say Henry Hertz as well? So this is another unit that you can have for this one as well. So it regards to, like, for example, how you can rearrange this one. So you can have, of course, a lot of things where you can get out of this from. All right, so remember this. These are the two main equations, and the unit for the coefficient of self-inductance, of course, it is basically called L, or just self-induction here. So how are we going to, of course, we can have Henry, that is also equal to Weber over ampere as well. So how can we define the coefficient of self-inductance L? Yeah. Okay, so we can say it is defined as the electromotive force created in a coil due to the variation of the current, let's say, by 1 ampere in each second as well. So this is one way to define this one, of course. There are some other ways as well, but where do we get this definition from? We can get it from the equation above. So basically, electromotive force equal to L, or we're talking about self-induction, so L equals to negative electromotive force, that is delta I over delta T as well, yeah? Don't forget this one. So we can say the coefficient of self-induction is defined as the electromotive force. Okay, here's the electromotive force created in a coil due to what? Due to the variation of the current, we can say, right? But how big of this current won't be? By the way, I can define it in two different ways here. We can say due to the variation of the rate of the change in the current. That is one way. If we go, let's say, by the by numbers, let's say, in terms of numbers, we can say if the voltage that is induced is 1 volt, the current that is induced basically that we have, or the change in the current that we have is 1 ampere per 1 second, let's say, then of course we get, let's say, 1 Henry. Okay, so this is going to be the definition of a Henry as well. So once again, we can say the coefficient of self-induction or inductance is defined as the electromotive force created, that is the electromotive force that is created basically in a coil due to the variation of the current by 1 ampere in each second. And that is, of course, comes from this one here. When the current, let's say, what current of a value of 1 ampere per 1 second changes, we can have, of course, we can have an induced electromotive force here. And of course, this is basically how you can define the coefficient of self-inductance. Okay, that is, remember, that was for a coil, yeah? What if it is a solenoid? That is also interesting. Remember this, for solenoid here, if it is a solenoid, or if we have a solenoid, as you can see, connected across a battery, the solenoid has number of turns, you can say, and of course it has a length, so the length is going to be A, cross-sectional area A as well. The length is going to be L, the cross-sectional area is going to be A. When the switch is closed, remember this, when the switch is closed, of course, the current grows from 0 to, let's say, a certain value here. So when this happens, of course, there will be a magnetic flux, you can say as well, yeah? So when we close the switch, the current is going to increase, yeah? If that is the case, the magnetic field also going to arise from this increase in current. So we can say this magnetic flux increase from 0 to a certain value, which leads to a creation. So when this happens, like I've told you before, there will be an induced, here's the, let's say, here's the direction of the current, yeah? So when this happens, there will be a current induced in the solenoid here. But the direction of this current is going to be in the opposite direction, because these two, using Lenz's law, will oppose one another. That is when you turn the switch on, yeah? But when you turn the switch off, it's going to be in the same direction here. But, okay, so put that aside for a second. So this current that is induced here will produce its own magnetic field, okay? This current that is produced will have its own magnetic field, but these two magnetic fields, of course, are going to oppose one another, which, of course, leads to, let's say, decrease the overall current over the circuit here. Okay, but it doesn't, for example, it doesn't stay like this forever. It is until the current is basically, or there is no change in current until the current gets into a certain value. When the current doesn't change anymore, there is no electromotive force generated. Why? Because this magnetic field doesn't change anymore. If there's no change in the magnetic flux, then of course there's no induced electromotive force, there's no opposition whatsoever. Okay, that is when we turn the switch on. If you turn the switch off, it is going to be opposite, and then the current will be, of course, flowing in the same direction. Okay, so during this period, the magnetic flux increased from this to this, 0 to a certain value, which leads to the creation of the induced electromotive force that opposes the original one. Okay, so how do we explain this one right here, guys? So let's move this one up a little. So we've learned that, okay, when we have, let's say, or the induced electromotive force, right, equals to what? Equals to obviously N, right? A change in the magnetic flux, you can say, over the time, yeah? But we've also learned that, okay, let's say using a coil or the electromotive force, you can induced, right, electromotive force or self-induction, let's say. So the electromotive force equals to negative L change of current divided by the time as well. Because these two are equal, so we can equalize this side of the equation as well. So we can say, let's save some space, and hopefully we can do that. So we can say negative N, because these two are equal, yes? Okay, so basically we can say delta, magnetic flux, change in time, equals to what? Equals to negative L, that is delta I over delta T. Okay, and of course now we can cancel out this 2 here. These two negatives cancel out. So what are we left with? We're left with negative N, you can say delta flux equals to L, that is delta I here. But remember this here. Normally, this magnetic flux, of course, we have, or the change in the magnetic flux, we said is going to be from 0 to a certain value, yeah? So it's going to increase from 0 to a certain value. Let's say flux 2, okay, or whatever you can call it, yeah? All right, so if that is the case here, so we can say that is for delta. For both, the same thing for the current as well. So it starts from 0 to a certain value here. So in this case, we can say N, that is basically flux minus 0 here equals to magnetic flux, obviously, and then L times, let's say, current to whatever final minus 0 here. So of course we can have N magnetic flux, right, equals to, or L, that is the coefficient of self-inductance multiplied by the current here. All right, so this is one of the equations that we have, and you need to know this equation right here. So number of turns multiplied by the flux, right, or the magnetic flux, you can say, and of course the coefficient of self-induction multiplied by the current. But remember this, when do we use this equation? Whenever magnetic flux is given or asked, then of course we can use this one. But watch this one here. So remember this equation. If we're going to use or complete this one right here, we can cover this one too. Watch what happens next, guys. Remember, we're trying to find this one for a solenoid, yeah? We do know that magnetic flux, right, equals to AB, yes? And of course cosine theta. We've learned this one before, correct? So we're going to use this one. So we can say NAB cosine theta, okay? And of course equals to what? Equals to L times I here. But we've also said that the magnetic field strength for a solenoid equals to what? If you remember, equals to mu naught Ni over what? Over L here. So of course we can substitute this into the equation. So what will it become? It becomes N, that is number of turns, multiplied by the area. And then of course we can say, if it is perpendicular, by the way, so we don't have to write, we go with this one for now. Okay, so in this case, of course, we can say, if it is perpendicular, we're not going to write this one, or perhaps you don't need this one, because if it is perpendicular, then the magnetic field strength, and of course, is going to be parallel to the area, or this angle is going to be 0, you can say. Remember, perpendicular to the plane of the area, okay? So in this case, cosine theta is going to be 0, and then of course we get, let's say we get this one as well, or maximum value. So in general here, we can say, I'm not going to write this one as well, considering the magnetic flux is perpendicular to the plane of the solenoid here. So in this case, of course, instead of B, we're going to write this one here. So this is mu naught, magnetic permeability, in space or area, you can say, multiplied by N, that is number of the turn for the solenoid, and then multiply by the current divided by the length. And on the other side, of course, we still have the coefficient of self-inductance, and then multiplied by the current here. So this current and this will cancel out. Okay, so what are we left with? So L, coefficient of self-inductance, equals to, you can see N, and N, of course, is going to be N squared, you can say. So we can say mu naught N squared cross-sectional area divided by the length. This is basically the coefficient of self-inductance for what? For a solenoid. So watch this. What does the coefficient of self-inductance in a solenoid depends on? It depends on the magnetic permeability, that's right. It depends on the number of turns, but remember, the number of turns is squared. So we can say it depends on the square of the number of turns. And it depends on the area of the solenoid as well. Hopefully I always kept solenoid, not a coil. So it is a solenoid. And then, of course, it depends on the length of the solenoid as well. And of course, you will see questions here now or soon. It says, by increasing which one of these factors, or by doubling which one of these factors, the coefficient of self-induction will change, or let's say will be bigger in this case. By doubling, watch this, by doubling the cross-sectional area or by doubling the number of turns. As you can see here, the coefficient of self-induction or inductance here. So L, it is directly proportional to N squared, and of course L is directly proportional to the area. As you can see here, because the number of turns is squared, so of course it would have a bigger impact on the coefficient of self-inductance here. So remember this, okay? So these are basically the equations that you are going to need here, or you're going to use, of course. Okay, so now we can ask this question here: what does the coefficient of self-induction of a or inductance of a solenoid depend on? Like we said, whenever you see questions like this, always write the equation, and then based on that you can tell what it depends on. So the first thing, it depends on the number of turns, but directly to the square of the number of turns, you can see, directly proportional. And then cross-sectional area, also directly proportional. And also the magnetic where's magnetic permeability, that is also directly proportional. But the length, you can see, it is at the denominator, so of course it's going to be inversely proportional, basically with the coefficient of self-inductance. All right, we have a question here. It says, like the question that I was just telling you about. It says, if the number of turns of a coil is doubled by winding another layer of turns above the original one and is in the same direction, okay, what happens to the coefficient of self-induction L? Remember this. We said because it is directly proportional with the square of the number of turns, so of course it would have a bigger impact. So if we double each one of these, or if we double the number of turns, then the coefficient of self-inductance will increase by a factor of 4, because if you double it, that means 2, but 2 squared, okay, because the number of turns is squared, so it's going to be 4 times. But if you just double the area, it's going to increase by 2 times. So doubling the number of turns, of course, would have a bigger impact or effect on this. So the coefficient of self-induction increases by a factor of 4. Okay. Now, we have a question here. Remember, it says an air solenoid. Let's solve this question together. So what do we have? Is it a coil or a solenoid? It is a solenoid, yes, because that is what the question tells you. Okay, now what does it say? It says an air solenoid of length 10 centimeter. Remember this. So we're going to change the length from centimeter into meter here. So we can say the length is 10 centimeter, that is 0.1 meter. Okay, and next it says cross-sectional area of 25 centimeters. So we have area, which is basically 25 centimeter. But remember, centimeter squared, yeah, because it is area. So how do we convert this one to meter squared? Remember this, we're going to write 25 as it is, but then centimeter squared is almost like 10 negative 2, but remember, since we have, because centimeter to meter, that is 10 to the power negative 2, yeah? But because we have squares, so of course now you can see that here, you're going to square this one. So in this case, it becomes 25 times 10 to the power, let me just erase this one. So it becomes what? It becomes 25 times 10 to the power negative 4. So let me erase all this and then make this one negative 4. All right, so negative 4 what? Remember, meter squared, because it is still area here. Okay, now what is given next? it says, and 400 turns, yeah? So the number of turns is 400 turns. Okay, next, by a current, so traverses by a current, so we have I, which is basically 4.0 amperes, or just 4 amperes for now. Calculate the magnetic flux, that is 1, which crosses the solenoid. Remember we said if magnetic flux or the change, not a change, if they are asking about the magnetic flux or if magnetic flux is given, there was a certain equation you needed to use, yeah? Do you remember that? Okay, very good. So magnetic flux, we said N times magnetic flux equals to what? Equals to we can say L times the current. Do you remember this part of the equation? So in order to be able to calculate magnetic flux, you need to have the number of turns, which we do. Okay, you need to have the current, which we also have, but we don't have the coefficient of self-inductance for solenoid. So let's find the coefficient of self-induction or inductance for solenoid. So we'll say L, coefficient of self-induction, for solenoid, not a coil. I hope I didn't say a coil again. Okay, so in this case, of course, we said mu naught, okay, multiplied by n squared, of course, multiplied by cross-sectional area divided by the length here. So do you remember the coefficient of the coefficient of magnetic permeability? Very good. It was 4 pi times 10 to the power negative 7 multiplied by, what is the number of turns? It is 400. But don't forget, it is 400 squared. Why? Because of this. And then, of course, we have the cross-sectional area, which is basically 25 times 10 to the power negative 4 meters squared. That is negative 4. And then divided by the length, which is in this case is 0.1. And of course, this one is about 5 times 10 to the power negative 3. Since it is L, of course, it is going to be Henry. Let me double check with this one here. Where is it? So I think I'll have, yes, that is basically what we have, yes? So it is 5 times 10 to the power negative 3 Henry. Okay, now we can go back to our calculation. So this is correct, basically. Now, after this, of course, we can find the value for the magnetic flux. So magnetic flux is basically equals to what? Coefficient of self-inductance times the current divided by the number of turns here. Remember, it is not squared anymore. So we can say L, that is 5 times 10 to the power negative 3 multiplied by the current, which is 4 amperes, and then divided by the number of turns, which is 400 turns. And of course, you do the math, you will find the magnetic flux. And this magnetic flux has to be in Webers because you've learned that magnetic flux is in Webers. That is for this one right here. Now, we're about to, so basically it's going to be 5 times 10 to the power negative 5. Keep that number in mind as well. Okay, 5 times 10 to the power, 5 times 10 to the power negative 5. Okay, Weber, or you can say Tesla meter squared as well. That is the answer for this. Now let's go back and solve the third part of the question, which says what? It says if the current is traversed during 0.1, if the current is reversed, my bad, during 0.1 second, calculate the induced electromotive force. Now, how do we calculate the induced electromotive force? But before that, what does it mean that the current is reversed? If the current is reversed, that means the direction of the current is reversed. So if it goes, for example, this way, which is 4 ampere, then if it goes the other way, that means reversing, that means the other way, which is going to be negative 4, if these are in amperes here. So what will be the change in current? We can say final minus initial, correct? So in this case, final is going to be negative 4 minus initial is 4. So of course we get a result or a total of negative 8 amperes. Now, the second part says, how do we calculate the induced electromotive force? We've learned that induced electromotive force equals to what? Equals to negative L, all right, multiplied by delta I over what? Over delta T. Very, very good. So in this case, we have negative. The coefficient of self-induction, we've learned that it is equal to 5 times 10 to the power negative 3. The change in current, we've said that it is delta I, it is negative 8, and then divided by this happened in 0.1 second, correct? Okay, yes, so this is also correct. So now you do the math, of course, you will get the, these two are going to be canceling out, so of course you get a positive value, and you do the math, of course, you get the value here in volt, okay? So that is, you can, or how you can find the induced electromotive force generated or induced, which is about 0.4 volts, or volt. Okay, now we have another question. That is a practice question. It says the electric current grows in a circuit from 0 amperes to 10 amperes during 0.1 second. If the coefficient of self-induction in the circuit is 0.02 Henry, calculate the induced electromotive force within the circuit. This is just the application of the equation, and that is what you need to do. Okay, so just remember this: electromotive force equals to negative L delta I over delta T. Find delta I, that is basically 10 amperes minus 0 divided by the time is 0.1 second. This value is also given 0.02, so you do the math, of course, you'll find the answer. Okay, now take a look here. That is also very interesting. It says, which one leads to a higher increase in the coefficient of self-induction of a solenoid? We've mentioned this one, I think, twice so far. Doubling the number of it is turns or doubling the cross-sectional area. We said because the number of turns is squared, so double that, you get increased, or coefficient of self-inductance increased by a factor of 4. But if you double the area, it just increases by a factor of 2. So of course, doubling the number of turns would increase the coefficient of self-induction more, you can say. Okay, so doubling the number of turns, because it is directly proportional to the square of the number of turns. Now, I want you to practice these questions. These are very, very important, guys. Remember, okay? Practice makes perfect. I'm not going to give you hints or ideas about this because these are basically everything that we went through. So I'll leave this one behind for you, or leave it for you, and I hope you practice. And of course, you always have the answers right here just to double check with your answers, okay? So you can see these are super easy. All right, so of course you will see that there are some questions that are very important, and of course I really want you to practice them. Okay, now let's talk about, as a matter of fact, perhaps we're going to keep this one or save this one for next time. Well, so basically next time we'll talk about eddy current, what is eddy current, and how eddy current will be generated, and what is the effect of eddy current on some other materials, or let's say devices that we're going to use daily. So, but that is for next session, inshallah. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.